Greetings, everybody from all around the world. This is Manoj Karkee from Washington State University, Center for Precision and Automated Agricultural Systems. Today, I'll be talking briefly about AI, machine vision, and robotic systems for fruit harvesting and fruit tree pruning. I'll talk briefly about why it is necessary or why it is essential, and then present a few research projects that I'm currently working on. And then at the end, I'll also briefly present my thoughts about where we are going in the future. Why automation in fruit production? It may not be new for many of you in the audience, but for those who are not familiar, harvesting and pruning and many other operations in tree fruit orchards are really labor intensive and laborious. They also pose human health and safety issues, risks for fall and other issues, as you can see from these pictures. And that's why it is important that we continue to research and develop technologies in this area. There has been long research and development in the past as well. However, we have not achieved the type of commercial success we would like to achieve, particularly again in specialty crops such as fruit and vegetable crops, where a lot of operations are still labor intensive. And the solutions we have developed in the past have not been commercially successful. To address these challenges, there are to develop solutions that might be commercially viable in the future. There have been a large number of efforts around the world in recent years, as you can see some examples here. Again, these example efforts are not exclusive by any means, but some of these universities in Australia, New Zealand area, region working in apple and green pepper and other fruit and vegetable crop harvesting. There are efforts in Europe and UK, also similar projects with robots picking, in this case here, green pepper, and there are similar efforts for apples and strawberries and so on. In terms of startup and other companies working in these automated machines, robotic machines. Here is an example from New Zealand, Robotics Plus. They're working in kiwi and apple harvesting. I have been working in this area for a few years now. There is a company down in Florida called Harvest Crew. They're working on and to some extent using these big strawberry harvesting machines in commercial fields. There is this company from Israel called FF Robotics, focusing on apple harvesting. I collaborate with FF Robotics, and we have a machine that has been tested in orchards here in Washington as well as in Israel in the past couple of years. I'll talk more about this effort in towards the end of the presentation. Another company called Abundant Robotics is also out of California. This company is out of California, and they're also working in apple harvesting with a real serious focus on commercializing in recent future. With all these efforts, we still face a few challenges or limitations in terms of developing automated robotic solutions. So far, I focused mostly on, or I presented examples mostly looking at fruit picking, but that kind of is true for other robotic solutions in orchard operations. For example, the robots that we have developed for pruning and thinning and other orchard applications face the similar limitations, such as lack of desired speed, accuracy, and or robustness. Sometimes these machines also cause produce or plant damage, and certainly agriculture runs in a really thin margin, and cost becomes an important factor. If the cost is high, lack of adoption becomes another bottleneck, and there is this cycle of high cost and low level of adoption, making it very difficult for these new technologies to get into the wider adoption. So to address some of these challenges, WSU Center for Precision and Automated Agricultural System program, particularly my research program in this center, has focused on various aspects of automation and robotics in fruit and vegetable crop production. In the next 10-15 minutes, 20 minutes, I'll be talking mostly about fruit harvesting and pruning efforts that are going on in my lab over the last 5-6 years. First, let's talk about apple and cherry harvesting efforts. In my research program, we're focusing on both mass and robotic harvesting system. When I say mass, it's more like a large number of fruit at a time. And when I say robotic harvesting, it is one fruit at a time, more like a pick and place kind of technology. When I say mass harvesting, just to repeat, it will be more like a second catch kind of system where, again, a bunch of fruit are harvested simultaneously and collected somehow. Different types of end effectors for both picking as well as sacking have been developed and tested in my lab, and different catching mechanisms, particularly when it is a mass harvesting system, and different robotic systems when we put all the components together into a system. We have tested many of those, or many different kinds of those in my research program. Here is an example of automated cherry harvesting. We started with a big cherry harvester, researched and developed by a USDA scientist about 2 decades ago, early 2000. And in my research program, we advanced or further enhanced this machine to improve the sacking mechanism as well as catching mechanism to maintain fruit quality and improve fruit removal efficiency. But at the same time, we have also developed a machine vision system that can capture images both day and nighttime conditions and estimate where these branches are that could be automatically grabbed and sacked to release these cherries. Robotic apple harvesting has been another major effort in my research program over the last, again, 5-6 years, maybe even longer. In this effort, we are evaluating or assessing how human pickers pick apples. We use different force and torque sensors and understand the forces involved in different fingers, the motion that is involved in picking fruit. We use those kinds of information to design different kinds of robotic hands or end effectors. We also have certainly developed 2D and 3D machine vision system and a fusion of those to detect and locate where target apples are, and have integrated everything together into a robotic picking machine. In this case, we see a custom designed and built robotic manipulator, and we see a soft robotic hand picking apples. Before I saw a quick video about this robot, I'd like to present some of the Bayesian algorithms techniques that were used in detecting and locating apples. As I mentioned earlier, we have color and 3D Bayesian system fused together to remove the background and remove the rows of trees that are not adjacent to where the machine is, and that simplifies the overall canopy environment for further processing and finding target apples. And certainly overlaying 2D and 3D is essential to locate those apples in the 3D space, so that the robotic manipulator would make a move to approach those apples. In addition to simple apple detection and localization, we have also expanded our algorithm using deep learning techniques, certainly, as we all are using certain kinds of deep learning models in our vision systems these days. We have identified all kinds of objects in tree canopies, including apples and branches and leaves and trellis wires and trunks. And in addition to that, we have also looked at the topological relationship between these objects, so that we can find out the obstacles and then accessibility to these fruit, and also identify the most efficient or safe direction for robotic arm and hand to approach these apples. As we can see in one of these apples here, if you are following my mouse in the lower right corner here, we identified the approach direction for this apple to be more the lateral to the branch that is right next to this apple, which is a safer direction for approaching. Otherwise, we might hit the branch and potentially drop the fruit on the ground, while may also be damaging the end effector itself. Hierarchical machine vision system, really simple, intuitive concept, but something really helpful to improve the picking efficiency. So here is the first image collected or captured of the canopy. Using the image processing system, we can detect some of the most visible ones and locate them. And the robotic arm would go pick them. And once the visible apples are picked, those behind would be more visible. And the second capture and second round of image processing would detect those and locate those, and the process and the picking would occur to the ones that are visible in this round, and the process repeats until there are any fruit left. So here is the prototype developed and tested in my lab over the last, again, 5-6 years, in collaboration with many researchers that I couldn't put names of in this short presentation. But as you can see, there is robotic manipulator custom designed and built, and there's this robotic hand or the end effector also custom designed and built using 3D printing technique. And in the second or the third version of the robot, we have a soft robotic hand, and that you can see in a little bit. In this particular prototype here, the fruit are being dropped on the ground, but in this second one, as you can see here, there is a collaborating catching robot, in a way, a simplified mechanism there to capture the fruit that is being picked by this new version of the robot. As you can see, it has a soft robotic hand picking apples. After we demonstrated the capability of this robotic picking system, we collaborated with FF Robotics. They were also working in apple picking area for a few years when we started talking, and then they had their experiences and a prototype machine. We had our experiences in a prototype machine. There are papers published, knowledge gained, and we joined our efforts together and wrote proposals together to build this fully scale machine and tested that into in different orchard environments here in Washington as well as in Israel. Here is a quick video of the So robotic picking is one effort, one kind of technology that I believe has potential, and I think it will make into the market fairly soon in the future. FF Robotics, Abandon Robotics, and potentially other companies all are pushing really hard, and I think there is a potential, again, there will be a commercial adoption of these technologies soon. Now, there are situations where I believe targeted second cats and other technology that I'm developing would be applicable for some of the varieties and some of the canopy architectures. In this particular, the promise with this one, however, is that we are harvesting a large number of apples at once, and the throughput of this harvesting process becomes really fast when we're using this kind of targeted second cat harvesting system. This is targeted because we're targeting a small section of the canopy rather than entire canopy, so that the fruit quality could be maintained by providing only a minimal amount of energy to just enough to release the fruit from branches and then capture them right underneath where they are. As you can see in this diagram here, ideally the design of this targeted second cat system looks like something on our top right corner. And then even in the realistic situation, if we look at the canopy architecture on our top left corner, um, it allows for a multi-layer targeted second cat system to function quite well, where the catching mechanisms could be inserted in between the layer of fruit that you can see in this particular tree canopy architecture. Here is a quick video that kind of demonstrates the concept. And this technology has been really promising for varieties of jazz and henry, I believe, where we have been able to keep the fruit quality really at a promising level. I think the best was about 10% on one of the varieties that we tested, and certainly the throughput, the amount of fruit that is harvested per unit time is higher than other in this example, we have only three catching mechanisms, but it could be extended to 7 or 8 or 6 or 7 or 8, depending upon the height of the tree, so that the entire canopy could be picked together, and the fruit quality could be maintained with a really short travel distance for the fruit from where they are to where the catching surface is. In addition to the harvesting efforts, our center has also worked on developing what we call bin dog, autonomous bin management or bin transportation machine that could drive to orchard roads on its own, find where the full beans are, pass over the empty ones if necessary, and pick those full beans and bring them out into the loading area. And this can also be used to actually deploy empty bins into those picking row. Right now, as we are trying to get stage, we have an empty bin being picked. As you can see, we are testing this in the dormant season, but you see the concept how a bin dog works, the one that we have designed and developed in our center, at our center. Before I close the harvesting efforts, I just wanted to kind of give a quick sense of what we are doing in robotic strawberry harvesting area. This project is led by Dr. Yunjun Su from University of Central Florida in collaboration with our team and Dr. Reza Isani from UC Merced. The concept here is to develop a modular, relatively small robotic systems that would use multiple hands to collaborate and pick strawberries in these canopies in the field environment. Certainly when the Uh, the strawberries are completely visible. Single arm and hand would be working independently, but when there is a situation, these berries are partially or fully hidden inside the canopies. We intend to use two hands to collaborate and open the canopy and pick strawberries. And that's the concept here. And again, these will be a swarm of collaborative modular robots picking apples, strawberries, and then also communicating among each other to optimize the overall harvesting operation. Next couple of minutes, I would like to talk about apple and cherry tree harp pruning efforts in my lab. Um, when it comes to pruning, it's very essential to understand how the pruning is performed and what branches to be pruned out and what would stay there. To develop these ideas and find simplified rules that could be implemented by the robotic system, we have discussed with growers and horticulturists, and also have observed professional pruners as they perform their job in the field. And based on those, for some tree architectures, we have started to put together pruning rules that would prioritize fruit distribution, uniform fruit distribution in these trees, which, by the way, would be also very much helpful for robotic picking, as pickers would perform much better when the fruits are uniformly distributed and have minimum clusters and have minimum fruit behind trunks and trellis wires and such. Pruning effort would help us create those kinds of fruit distribution that would be again friendlier for robotic picking. Here is a quick video of our lab evaluation of the robotic system. As you can see, this is a UR5, Universal Robotics 5 manipulator that is being used here. It has been slowed down so that we don't risk the, or at least minimize the safety issues here. But you can see the concept that you can go to the target branches and it can cut them off. In addition to manual pruning point selection and movement of approach of this manipulator and manufacturer to target branches and cutting those off, kind of a proof of concept in the lab, we've also started putting together a machine vision system and decision support system to autonomously select cut points for these robots. Here is a quick example of how tree architectures are built using the machine vision system that we have used, and then that leads to estimation of geometric parameters such as the length and the diameter and things like that, and then we can use those as a guidelines for us to detect which branches to prune out. In this specific architecture, all the branches that are growing laterally from those vertical branches would have to be pruned out, and that's why those yellow branches are identified as the ones that needs to be pruned out. Here is the complete integrated system put together using, again, Intel RealSense cameras, as you can see, and a little scissor cutter, pneumatically operated. This was tested in the field this last winter, but we couldn't be as successful as we wanted. So we're continuing to improve it, and we'll go back to further evaluate this system. So before I close, I'd like to briefly talk about some of the challenges that we're facing in this area of automated and robotic field operations in apples and cherry orchards. And for that matter, that might be similar to all kinds of tree fruit orchards or tree-fruit crops, and where we might be going in the future. So achieving high harvesting efficiency and pruning efficiency, um, related to speed, being fast enough and economic at the same time is always a challenge in automating or using robotic systems in orchards. For example, when we talk about robotic picking, even in the modern orchards, we are only about 65% removable efficiency with FF robotics, at least the robotic picking system that I have developed in our lab, and and if it is a conventional orchards, it would be even worse, and I think it's not that practical for us to use the type of system that we have tested so far. Speed, complexity, and cost is another aspect. We want our systems to be really fast, but at the same time, they need to be really simple and low cost so that they can be adopted by the farmers. And fruit quality becomes another issue in some certain, when we are using certain kinds of technologies, and keeping fruit quality to the desired level is essential. And I think we need to further investigate our technologies, improve our technologies to achieve desired fruit quality. Human machine collaboration could be one way we could help. For example, um, I don't know how do we put it when we say human machine collaboration. It could be side by side, it could be machine followed by human, but both in the vision decision making system as well as in the real field operation, there could be human and machine collaboration so that the efficiency could be improved to close to 100% as desired by the farmers. Soft robotics could be another technology that might be helpful to minimize, for example, fruit quality. Improve fruit quality and minimize the complexity and cost associated with these robotic systems. And certainly, we need to continue to exploit the capabilities of transdisciplinary teams and developing systems approaches. With that, thank you very much, everybody. If you have any questions, I have my email address down here on our lower left corner. I would be glad to converse, communicate with you in any way possible in the future. Thank you very much for your attention.